Welcome, everyone. I am Antino Kim from Kelley School of Business at Indiana University. This is a joint work with my co-authors, Professor Mo-Chen Yang and Professor Jingjing Zhang. You've probably already heard a lot about the promise of AI. Across different domains, predictive algorithms have been shown to outperform human judgments. Even in areas that were once considered to be reserved for humans only, we are witnessing examples of algorithm superiority. But in many application domains, it is still humans who decide whether or not to rely on algorithms for decision making. Despite the evidence of algorithm superiority, people often avoid using algorithms, relying instead on their own judgments, which are often less accurate. People's reluctance to use algorithms in favor of human judgments poses a challenge for organizations aiming at making more accurate and informed decisions, as well as for firms that develop and sell algorithmic tools. And this problem gets worse when algorithms make errors. Because real-world situations are often far from perfectly predictable, even the best predictive algorithms produce imperfect predictions and occasionally make substantial errors. Errors are, in a sense, a natural part of development and use of algorithms. You may be familiar with class imbalance problem where there aren't enough testing data for certain cases, and the typical trade-off between exploration and exploitation. Predictive algorithms sometimes need to choose between making safer decisions that have worked well in the past and exploring riskier options that might potentially lead to substantial errors, but also to a greater return. Errors also have a close connection to the decision of how much to train and test the algorithm. Some vendors may choose to release early versions of software and make improvements later. All these decisions affect when users are more likely to encounter an error. And our objective here is to build upon what we already know about the effects of error. An error in this context refers to a substantial mistake made by the algorithm that is far worse than its expected performance. While it's been found that errors lead to algorithm inversion, we posit that not all errors affect users' reliance on the algorithm to the same extent. Specifically, given how there are decisions that can affect when users are more likely to encounter an error, we focus on the timing of errors. Users may encounter an error when they start using the system, or they may encounter an error after having used the system for an extended period of time. And we are interested in, as the title of our paper suggests, the differential impact of early versus late errors on users' reliance on algorithms. In the interest of time, let's dive right into our first study. Participants completed 20 rounds of prediction tasks, and the payment from the experiment was based on the accuracy of those predictions. For each task, the participant first viewed the amount of rainfall, fertilizer, and sunshine, and made an initial prediction of crop yield. Then the participants were asked to choose whether to use their initial prediction or rely on the algorithm's prediction for the task's final prediction. So the final prediction equals the algorithm's prediction if the participants chose to rely on the algorithm. Otherwise, it was the same as participants' initial prediction. Upon completion of each task, the participant got to see a performance summary, which included the true crop yield, the algorithm's prediction, the error of the participant's final prediction, and the participant's mean absolute error so far. The algorithm's prediction for each task was only displayed on this performance summary page, so reliance on the algorithm represents a full delegation of the decision to the algorithm. So reliance is a binary decision here. The participants were also provided a table with 10 example records, which offered a preliminary understanding of the prediction task and the general prediction accuracy of the algorithm. This is the true yield generating function, which depends on RFS, the amount of rainfall, fertilizer, and sunshine. And the calculated yield was rounded to the nearest integer. Each of the three inputs took an integer value from 1 to 25 and was randomly drawn from that range. This particular functional form, there's nothing magical about it, was chosen to simulate a non-intuitive prediction task. There was where the inputs were related to the output in a non-linear fashion, and the specific coefficients were picked so that the yield also largely fell in the same range of 1 to 25. And this is how we design the predictive algorithm. It generates the predictions based on the true yield with random deviations drawn from the range of -2 to 2. So the prediction was unbiased and had a deviation no larger than 2 units. And this outperforms an average participant, so relying on the algorithm would generally lead to a better predictive performance and would be beneficial to the participants. The participants were randomly assigned to control, early error, and late error groups. The control group saw no significant errors, and the algorithm's predictions were always within the 2 units of the ground truth. But for the early error group, the algorithm's prediction was off by 10 units in the second round. Regardless of whether or not the participant chose to rely on the algorithm the error round, the participant always saw the error occurred in the summary page. And for the late error group, the algorithm made a significant error in the 12th round. We chose round 12 in order to give participants enough time to become familiar with the algorithm and build confidence in its prediction quality. And we also wanted to have enough distance from the point of early error. Post hoc analysis shows that participants in the control group were significantly more likely to rely on the algorithm's predictions after 10 rounds than they were at the beginning of the experiment. So that lends support to choosing the 12th round as the late error treatment round. We recruited 300 participants from MTurk, and the various statistical tests we ran showed that the random assignment was successful. Here is a model-free evidence of treatment effects. This shows the percentage of participants who chose to rely on the algorithm's prediction for each task, and there are a few things worth noting here. There's a clear drop in the reliance on algorithm prediction immediately after the treatment rounds, and the drop was especially steep for participants in the early error group, and their overall reliance remained lower in all subsequent rounds compared to the control group. In contrast, though the reliance dropped in round 13 for the late error group, it quickly returned to a comparable level with the control group in the following rounds. We next analyzed the treatment effects on algorithm reliance using regression methods. We used a relative time difference in differences logistic regression specifications. Let me just highlight some of the most important parts here. The dependent variable reliance is a binary indicator variable, rely or not, and treat indicates whether the participant is in the control group or in one of the treatment groups. The after variables are dummy variables that indicate post-treatment rounds. The interaction terms between the treatment group indicator and the post-treatment round indicators capture the treatment effects of the algorithm error on each post-treatment tasks. Basically, the coefficients of these interaction terms will show us the effects of early errors and late errors. We also control for characteristics of participants and prediction tasks, such as gender, age, and the task round index. Here's the result, which is dense. So let's visualize the most exciting part. As I said before, the interaction terms are what we are most interested in. The results, the estimated coefficients from the previous table, is shown graphically along with their 95% confidence interval. From the negative and significant coefficient, we can tell that there was a steep decline in reliance immediately after the early error. The late error group, this effect is marginally significant at 10%, so clearly the early error had a greater impact on reliance than the late error. Scanning through the rest, we see that the effect of early error persisted and there was no stable pattern of recovery. The reliance level was pretty consistently lower than the control group. In contrast, the late error did not have such an effect. In addition to evaluating these coefficients over post-treatment rounds, we also created a novel metric for reliance recovery. For this, we counted the number of post-treatment rounds before the participant started to use the algorithm's prediction for k consecutive rounds. Intuitively, using the algorithm continuously for multiple rounds signals a participant's reliance on the algorithm, and the parameter k controls the strengths of the reliance. For example, suppose a participant in the late error group made the following choices between using the participant's own predictions and the algorithm through the 8 post-treatment rounds. An error occurs here, and the participant does not use the system, not use, then use, and so on. If k is set to be 2, based on our measures, we see that it only took 2 rounds for the participant to restore reliance. We see here that regardless of the value of k, it took significantly more rounds for participants in the early error group to begin relying on the algorithm than those in the control group. In contrast, the difference between late error group and the control group was insignificant. This once again shows that users' reliance on algorithm recovered significantly slower following an early error than a late error. In the second study, we explored whether giving participants the option to make adjustments of their own predictions after viewing the algorithm's predictions would affect their reliance on the algorithm. Overall, the procedure of study 2 was similar to study 1, except here the participants could adjust their final prediction after seeing the algorithm's prediction. So the design of study 2 reflects a more collaborative interaction between human and algorithm rather than a complete delegation. Once again, we recruited participants from MTurk and we verified that the random assignment was successful. I always like to start off with a model-free demonstration of results. This shows whether or not the subjects adjusted her prediction after seeing the algorithm's prediction as a binary measure of reliance. Compared to what we saw in study 1, right off the bat, we see that the lines are more crisscrossed, indicating that the effect of errors and the difference between early and late errors are not very pronounced. We also see that the highest number of participants adjusted their initial predictions in the treatment rounds, likely because the substantial error misled participants to believe that their initial predictions were far off. We estimated the same logistic DID regressions described previously. Here we don't see any significant reductions in the choices of making prediction adjustments throughout the experiment, even in the round immediately following the treatment. Though there are a couple of minor dips in the late error group, given that there was no significant effect even in the immediate post-treatment round, it is unlikely that they were due to our treatment. We also considered how much the participants adjusted their predictions as a more granular, continuous measure of reliance. Basically, we considered the degree of adjustment made towards the algorithm's prediction. And the patterns are similar to what we saw with the binary measure of reliance, including the high level of adjustments during the respective treatment rounds. We once again ran the same DID specifications, but as linear regressions this time, since the dependent variable is continuous. And the patterns are pretty consistent as before. There's no significant reductions in the reliance level, even in the round immediately following the errors. And there was no result that we can attribute to the errors. Overall, when participants were given the ability to adjust their predictions based on the algorithm's predictions, their reliance on the algorithm was minimally affected by the error, even if the error occurred in the early stage. Our particular focus on the timing of errors stemmed from its theoretical importance, no one has looked at it yet, and also from its intimate connection to practical considerations of algorithm design and implementation, such as when to explore potentially risky decisions and how much to train an algorithm prior to offering it to end users. We found that early errors are more detrimental to users' reliance on the algorithm than late errors. Early errors lead to a greater dip in the level of reliance, and the post-error recovery is also notably more stagnant. In fact, in the early error group, we did not observe a stable pattern of full recovery in users' reliance during the entire duration of our study 1. Hence, in weighing between exploration and exploitation, our results suggest that it may be better to postpone the risky explorations until users have become familiar with the system and are more forgiving of the errors. Although the literature mentions some benefits of releasing early versions of software and patching later, such decisions should also consider the cost differences between early errors and late errors. Now, sometimes early errors are unavoidable to collect enough usage data, for example, or there may be great benefit to taking risks, such as releasing the tool early and start reaping the benefit instead of keeping it in the training and testing cycle. In that case, giving users more control can mitigate the risk associated with early errors. Doing so effectively closes the gap between effects of early and late errors. This result points at a possible implementation strategy where the system asks for users' confirmation during the early stage of deployment to guard against the negative impressions from early errors. And once the system matures, such a crutch can be removed. Well, that was my talk. That's a wrap. Thanks for watching.